Recorded is rolling. Welcome to Monday, April 11th. You guys remember back on Thursday, Friday, we're starting electricity, did electrostatic force, some electric field, and we started on circuits. I did some demo stuff. So we're going to pick up there, do more circuit. Now, before I get going too deep in class, since this is a fifth period, see some of you guys brought in more registration packets. If you do, pop the gray tray. I'll take that to guidance. Those are technically due in a few days here, 14th, right? Also, for AP, here's our plan is I'm going to take this week to do electricity and circuits with you guys. We only have a 4-day week. You guys know we don't actually have school Friday. Then what I'd like to do after this week, unless there's something like spillover, I really have to do with you guys, is go back into review. So we got to review unit 6 and 7, and then do some practice exams. So that's going to take us all the way to May 12th. Now, I'm not going to have any like formal homework for you guys this week. Right? I want you guys to learn circuits, be familiar with it, see it, do some stuff with me. But you guys know there's all those AP classroom assignments that are open. Right? There's opportunities for you guys. So that's independent learning. So are you guys doing those on the weekend? Are you guys writing your planner? Giving you guys selves a space and time to do those? Right? There's all those learning opportunities. I think this. All right, but we'll take these 4 days to do circuits, and possibly Monday I'll see if there's something else I have to do with you guys. But here we go. Right, so you guys just got a page, has some circuits on one side, has some waterfall models on the other side that we won't get to today, but eventually. Okay, we're going to do a bunch of circuits, series and parallel, and then tail end of class today, I'll go over Kirchhoff's laws with you guys. We're going to start digging into the internal workings of a circuit. How exactly does the electricity flow around? How does the current split? How does the voltage drop? If you have some complicated circuit. But let's look at these two guys here painting the fence. And how does this tie into electricity? And it will. So say Alan here can paint a fence by himself in 3 hours. He's looking at this fence and, oh, it takes me 3 hours to paint this fence. Bob could paint the whole fence by himself in 4 hours. Bob's a little slow. These two guys are going to make a two-man team. If they make a two-man team, how long would it take them to paint the fence together? Who knows either the answer to this question or how the process where how you could solve it? Does anybody know? Yeah.
Is it 1.7 hours?
1.7? You're gonna say 1.7? Yeah. Okay. So Stefan and Brock know 1.7 hours. Okay. How do you know it was 1.7 hours?
I did like percentage over time.
Oh, you really did from scratch. Okay. All right. Okay. So I know the math to solve this, but yeah, there's a theory of why this works that I forget. But yeah, if you ask Stefan, he knows the theory of why this works. All right. So well, let me before I actually show you guys how to solve this, show you guys a cool technique that a lot of mathematicians use to hone in on answers to unsolved math problems, because there are a lot of unsolved math problems out there. And what mathematicians will sometimes do is they'll say, well, we can create proofs to create boundary conditions. So we can say, well, it has to be at least this big and at most this big, and it's got to be somewhere within this window, the answer, whatever complicated question. How about this? What if it took Alan 3 hours and Bob also 3 hours individually, and they make a two-man team? How long would it take them as a team? 1.5, right? What if it was 4 hours and 4 hours to make a team? How long? 2 hours. So doesn't the answer to my exact question have to be somewhere in the window of 1.5 to 2 hours, right? And of course, you guys know the exact answer is 1.71 hours. Okay? Right, so I'm gonna show you guys two different ways to solve this. Right, one is this way. 1 over the total time that we're interested in is 1 over Alan's time plus 1 over Bob's time. Okay? So 1 over the total time is, see, Alan was 3. Leave a little space here. Bob was 4. Okay. Fractions. If you're adding fractions together, you need a common denominator, and a common denominator here is 12. So multiply this guy 4 over 4, multiply this guy 3 over 3. Okay. So 1 over the total time is 4 12s plus 3 12s. Okay. That's going to be 7 12s, which is not the answer yet. It's 1 over the answer. Okay. So last step, you guys have to take the reciprocal. So the total time would actually be 12/7 hours if I did listed my unit this whole time. Okay. And yep, that is about 1.71 hours, which is indeed inside that window of 1.5 to 2 hours. Right? That's it. Yeah, 1.71 hours. Right. Now, what does this have to do with electricity and circuits? Actually, I bet there might be a couple of guys out here who know where I'm going with the story with the guys painting the fence. Right, what does this have to do with circuits? Okay. How about this? Do you guys like my new posters up here? See any posters that might look like those notes at all? So remember, so we started with some circuits, right? And there are different ways you can wire up resistors. Okay. So here, quick demo. I've got 5 volts resistor, right? But here, oh, look at that, it's bright. Or how about this? 9 volts resistor, right? Voltage source resistor. Boom, it's bright, right? Or if you put these two, see these two guys would be in parallel with each other. The electricity is pushed through both simultaneously. Ooh, now they're both really bright. Ooh. But if you chain them in series, like sequential, one after another, ooh, they're both kind of dim. Look at that. Okay, so there are different ways you can wire up resistors. They can be in series, they can be in parallel. What's the rules for finding equivalent resistance in each of those scenarios? So equivalent resistance. So start in series. Okay. Now series setup, just sequential, just one after another. Okay. What I'm doing with these notes here is I'm saying I'm clipping these two resistors out of, it's supposed to be jagged like resistors. Okay. I'm clipping these two resistors out of a larger circuit. So notice I didn't actually draw the voltage source, but maybe these are connected to the voltage source, or maybe there's like 50 other resistors and it's all wired up all crazy. Okay. So I'll call this resistor A and resistor B. For example, this might be 3 ohms and 4 ohms. In that case, the total equivalent resistance from this lead to this lead, like how much are you pushing against? Well, you just add them together. Resistor A plus resistor B. So for this number example, it's 3 ohms plus 4 ohms is 7 ohms. Boom, done. Right, 7 ohms. Right. If you're on a street, traffic analogy, right, driving along the street, you see 3 stoplights, you see 4 stoplights, and it's all along the same road. Well, didn't you just face 7 stoplights? You had to go through all 7 stoplights. Okay. All right, now let's switch over and look at a parallel setup. Parallel. Resistor A, resistor B. Oh, I should have put numbers on these. So let's call this guy 3 ohms and 4 ohms. Right. Just arranged, so that the electricity would be pushed through both simultaneously, and it's parallel, right? So you got series versus parallel. Okay. Now this one, what was the equivalent resistance? Well, it goes like this. 1 over the equivalent resistance is 1 over RA plus 1 over RB. Hey, this is the same math as 2 guys painting a fence. Okay? In fact, 2 guys painting a fence, it's like they're working in parallel. Just like these 2 resistors. Okay? And we already did the math for this. So at the end of the day, the equivalent resistance is, well, for 3 ohms and 4 ohms, it's going to be 1.71 ohms. Okay? Notice the more resistors you add on in parallel actually decreases the total resistance, right? Because sort of like a traffic analogy, every time you open up a new road, right, even though it has its own stoplights, it does give you more options to drive, right? So then the traffic splits and it's easier to drive. There's less total resistance, right? Now, you might be thinking, like, if you're sitting here solving these all day, let's say you're an electrical engineer or an electrician, right? You see resistors all over the place. Okay, I got to do this calculation again for like the 200th time. Okay. You got this process, follows common denominator, blah, 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 blah. Do you think that there might be maybe an easy method where you could just skip straight down to this answer right here? Or like the setup? I mean, just cut through all the common denominator stuff, okay? There is, like the 12 and the 7, hey, isn't that like the product over the sum of like the hours of the guys painting the fence, or in this case, like two resistors in parallel, right? So here's an alternate way to solve parallel, but there's a catch. So if only 2 resistors in parallel, then the total equivalent resistance equals product over sum. Or I could say like this, RA times RB over RA plus RB. Okay, just to show you this does work. Right? So the numbers were 3 and 4 I've been using over and over. So maybe it's 3 ohms and 4 ohms. 3 times 4 over 3 plus 4. Or maybe it's 3 hours to paint a fence, 4 hours to paint a fence. Like these guys paint a fence. Right? 3 times 4 over 3 plus 4. Okay. Either way, it's 12 over 7 is 1.71. Okay? And if I'm talking about resistors, of course, it would be ohms. So this would be like ohms of resistance. Just like we've been getting all along for 2 in parallel. Guess that? Okay. Now, I do want to emphasize this is only for 2 resistors in parallel. Okay. So here's a sort of a counterexample. What if I brought in a third guy, Chad, to help paint the fence? Okay. So could I use the, do you think if I did the fraction method, I could do +1 over Chad and then just solve it that way? Yeah, that'd be totally fine. Right. And if I brought out some more guys, I could do +1 over Derek, +1 over Eric, +1 over Ferric, right? And just like keep going, right? But if you want to do product over sum, right? Well, you can only do 2 at a time. Now there is a sort of a workaround where you can do the product over sum method. Oh, where's my product over? Where you can do product over sum method for like multiple resistors or multiple people painting the fence, and that's just to chunk it down to smaller parts. So say we did have a third guy, Chad, okay? And let's say Chad could paint this whole fence in like an hour because he's Chad. That's what he does. Well, what I would do is for the 3-man team with product over sum is I would just take Alan and Bob by themselves and do product over sum, get 1.71 hours. And then I would incorporate Chad an hour and do product over sum between these 2 guys collectively and Chad, right? So I can do product over sum and then another product over sum, just chunk it down to smaller parts. Right, you guys get that? Right. And we'll work out some of those in class pretty soon right here. Okay. Any questions so far? Okay. Now this is just finding equivalent resistance. We're going to take a lot of class today to find equivalent resistances. Okay. The next steps would be things like I'm going to go into Kirchhoff's rules by the end of class today. Then you could go a step and say like how much current flows from some voltage change, right? Whether you're talking about 9 volts or 5 volts, right? How much current flows. And you could go another step and say like how much power, right? And you can dig into the circuit and say, well, how much power across each resistor? I'm getting towards like the backside of this page with all this fun stuff going on. Okay. So we're eventually getting there, but one step at a time here. Okay. Start with this right here. Right. We're just going to solve these and do Kirchhoff's rules, and I'll take us to the bell today. Okay. Right. So you guys see this very simply. Right, 2 parallel lines, one shorter than the other. There's your voltage source. Okay. Like so many volts. Okay. And then jagged. That looks like a resistor, like this guy right here, this resistor. Guess that? Now, number 1, I won't even write this down on paper. The total resistance of that circuit is just the resistor, right? Like mine says 1 ohm, so I'll just circle 1 ohm. Boom, done. Okay. Guess that? How much resistance does that battery feel like it's pushing against? Well, just that resistor, and that's it. Because the wire itself has almost no resistance. Okay. All right. Number 2. All right. I see 2 resistors, but I have to figure out, is that a series or a parallel relationship? Because that would lead to different outcomes. Okay. So here's what I do. I start at the voltage source. I'm going to start tracing around like I'm the current flowing, right? Do you guys see how all the current has to go through R2 and then all the current has to go through R1? Or if you go backwards the other way, it's the same story, R1, R2. But it has to go through both sequentially, and there's no skipping any resistors. right? That means it's a what relationship? Series or parallel?
Parallel.
Series, right?
I
Right. Here, yeah, a lot of people have been saying parallel today, but this is like your guys' second circuit you've ever seen. So that's right. If you skip down to number 4, you guys see number 4? Right.
Yes.
Yeah, number 4 is parallel because see how if you're tracing around a circuit, so you start the voltage source, and you're tracing around, blah, 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 and then you hit this junction, and at this point the current splits, and part of it goes this way, and part of it goes this way, right? And then it all comes back together, right? So the electricity is being pushed through both simultaneously. That would be a parallel setup in number 4. Right? I want to throw you guys out a question that's going to come back at the end of class today. If the current does split in number 4, which way do you think most of the current goes? Through the smaller resistance resistor or through the larger resistance? Probably through the smaller, like path of least resistance, right? Now, it's probably going to be a proportional split, right? Maybe some of the current goes through the larger resistor, but maybe most of it goes through less resistance. Right? Yeah, that'll come back by the end of class today, but we're getting a little bit ahead of ourselves. So let's go back to number 2. So I see 2 in series. Oh, I was going to wire these up for you guys too. So let's take a look at where's my bulbs? Here we go. 2 in series. All right. Ooh, looks not as bright as just the 1. Right? It's a little dimmer, right? But you just add those together, right? Can you guys do that plus that? So for me, you got 3 plus 4 is 7. Boom, done. You guys got a number 2? Right. How about number 3? Those 3 resistors are connected how? Also in series, right? So can I just add those together? Right. This one I go ahead and write down. Right. So I'm gonna write down number 3, even though you guys can do it in front of you anyway. But in case someone is watching this video on mute in the future, like what's going on? Right. Number 3, the total equivalent resistance is just R1 plus R2 plus R3 because they're all in series. So for my paper, it's going 7 ohms, 8 ohms, 9 ohms, 15, 9, it's like 24 ohms. Okay. Boom. Okay. If you knew how many volts that was, then you could also calculate the current, maybe using Ohm's law, right? I equals V over R. Right? Actually, all these questions down here ask you to do that. I give you the voltage source, say how much current flows. But right. So far, we're just finding equivalent resistances. All right, and then what does that look like? You guys see I got 3 bulbs here in series, one after another. Okay. Oh, how about this? Here's all 3. Ooh, look at that, really dim. Right. What if I take this lead and I switch it right here? You guys see that the bulb that's not lit is not even part of the circuit, right? Because no electricity even flows through this guy. Okay. And if I take this lead and move it all the way over here, look at that. I have only 1 bulb that's even in the circuit, and it's really bright. Ooh, look at that. 1, 2, and hey, go. 3. I see 1, 2, 3. Ooh, look at that. Okay. All right. All right, number 4. Okay, you guys told me that's in parallel. I'm just gonna cut straight to the product over sum method for this one. For number 4, so the equivalent resistance is R1 times R2 over R1 plus R2. I could definitely do that because there's only 2 of them. Cuts through all that common denominator math. So the 7 times 8 over 7 plus 8. Please put my number of ohms. Say, all right. You guys got a number 4? Everybody right? Okay, now number 5. Okay, now this one, a few didn't talk about, but yeah, start with this. Those 3 resistors are connected how? Yeah, you guys didn't think in parallel? Oh, I forgot to show you guys this. Okay. So here's 2. Oh, this guy lost it. Oh, I think this is starting to fall apart. Man. Yeah. Well, I can barely get going. I see 2. Yeah, they're getting a few years old now. Where's my 3 in parallel? Yeah, so here's number 5. I've got 3 in parallel. Ooh, look at that, all super bright. I'll tell you guys what too, I do want to get you guys in the lab area with these Christmas lights and cell phone chargers. You don't want to do more than about this many in parallel. Like if you did like 7 or 8 in parallel, it looks really cool because it's got a bunch of bright bulbs, but then it burns out the cell phone charger. Poof. So yeah, don't want to do more than about 3 and just be safe. Okay. So one way you could solve number 5 is just to do the reciprocal method with just add a bunch of chains together. So let's start with that. Let's do that. You guys can do that. See what you get. 1 over R total, or R equivalent resistance. You could just go 1 over R1 plus 1 over R2 plus 1 over R3. Ohms, ohms, ohms. Okay. I'm gonna let the calculator crunch this just to avoid doing a bunch of common denominator math. See that plus that plus that. Okay. So 1 over equivalent resistance now is this tiny, but this many 1 over ohms is the unit. Okay. Now that's not the answer yet. If you want to figure out the equivalent resistance, what's the last step you have to do? Reciprocal. Yeah, so the actual equivalent resistance, of course, would be the reciprocal of that. Okay. And one way you could do 1 over the answer or 1 over and type that number. Okay. There's also, do you guys see above the 7 key? There's an x to the -1. Okay. You could just hit that key, boink, and that'll get the answer for you too. Okay. So here, this right here is the same thing as if I go boink. Just take the reciprocal for me. Okay. So that ends up being, for my numbers, this many ohms. Okay. Notice that the equivalent resistance in parallel is smaller than any of the resistors individually, right? You know, if it took this guy 8 hours to paint a fence, this guy 10 hours, this guy 12 hours to make a 3-man team, well, they're going to finish it faster than the slowest guy, or faster than the fastest guy either. Right? Right. Yeah. All right, now I want to do the product over sum method. Now remember, product over sum you can only do 2 at a time. But I need to introduce to you guys the next critical part of solving circuits that I don't think I've told you guys yet, which is going to be really important for these down here. Ooh, let me hit the pause on this recording.
All right, and we are back.
All right, so to solve some of these more complicated ones, I'm going to introduce this idea right here, although technically you could ignore it, but this is going to be important later, okay? Is this particular method, right? So from the point of view of this voltage source, how much resistance total is it facing? Well, you know the answer already because we just did the reciprocal method, but here's the process. I'm going to fly over to the opposite side of the whole circuit. So I'm looking at R3 is the furthest from the voltage source, okay, set. I'm going to work my way back towards the voltage source and find equivalent resistances along the way. So just usually do like 2 resistors at a time, right? Until you get back to the voltage source. Okay. So this might seem kind of silly for this one because it's pretty straightforward, but this will be really important when we get to like complexity down here. Okay, so let's do that. I see R2 and R3. Now, are those in parallel or series with each other? Parallel, right? Okay, kind of know that already. So let's do that. Okay. So what's the equivalent resistance of just those 2 in parallel? I'm going to cut straight to product over sum. So here, I'll write down this for completion. Product over sum. Okay. So I'm looking at 10 ohms, 12 ohms, 12 ohms. All right, some crazy number. Okay, 120 over 22 looks like. Okay. Yeah, I mean, if you're an electrician, right, see these 2 resistors, you do okay. 120, 22, boom, boom, done. Right, so this many ohms. Right. Then what I'll do, now that's not the answer yet. Right? That's one step of a process. What I'm going to do is redraw the circuit. Redraw the circuit. And find an equivalent circuit. So I got my voltage source here. I've got R1 that I haven't touched yet. And R1 for my paper says 8 ohms. Okay. And then R2 and R3 collectively, well, it's as if there's one giant 5.45 ohm resistor right there. Right? This is R2 and R3 put together. Okay, you guys got that? Ah, and then between this and this, those two are in also parallel with each other, right? Kind of do that from the outset. Okay? I can do product over some of those. So now the total equivalent resistance for this whole circuit is the product over sum between these two numbers. So this times this over this plus this. Number of ohms. Oh, and it's the same number we got before. Okay, using the reciprocal method. So same answer. Okay. Guys good there? Then yeah, just think ahead to like later this week. If you knew how many volts this was, you could apply Ohm's law. Here, I'll just look that down just so you guys remember this from last week. You guys remember that the current that ends up flowing is equal to the provided voltage divided by the total resistance. So then this number would just feed in right there. Okay. If I knew it was like, oh, it's 9 volts, take 9 volts divided by that, I'd know how much current was flowing through. Right? All right. Great, guys ready for number 6? Number 6. Right, let me zoom in here. Right, number 6. Yeah, actually, if you look at number 6 and number 7, it's okay. They each have 3 resistors. There's some combination of both series and parallel, but they're wired up differently. Maybe I should just break out both of them right here so you guys can see number 6 and number 7 next to each other. Okay. So I'm thinking number 6, I see one resistor is directly connected to one of the leads, and the other 2 resistors are simultaneously connected to the other lead. You guys see that for number 6? Okay. So that would look exactly like this right here. Okay. Now this is my light bulb example is actually a little bit simplified because all the resistors are exactly the same number of ohms, right? But I wonder what this would look like. Light this thing up. So here's my R3. This guy's my R3, right? And my R1 and R2 in parallel with each other over here. Look at that. There's a really bright R3 and an extremely dim R1, R2. Now they have to be on because electricity has to be thrown into them, but you can barely see it, right? You guys see that? That's number 6. Hey, I wonder what number 7 looks like, where it looks like R3 is directly connected to both leads and R2 is connected to one and R1 is connected to the other. Right? That would look like the way you can make that is to do, oh, whoops, that's the wrong one. Here, this one right here. Okay. It's to make like an equilateral triangle, okay? And then just connect 2 of these. So the I'm going to have this left bulb as my R3 on number 7. Okay, so connect this here, connect this here. Okay. All right, so again, I've got one bright one and 2 kind of dim ones. Right, my R3 is the really bright one. But you guys see that the dim ones aren't as dim as they were back in number 6? They're kind of like medium type brightness, right? Okay. Now, what is the physical quantity you'd be looking at to determine how bright is something? That is power in watts, right? And we're definitely not going to get there by today, but I'm just thinking ahead a couple of days here. Right? So if you're asked like, what is the brightest bulb? Then you're going to look for, well, what has the most number of watts going through it? Okay. All right, so number 6. All right, let's use that method that I just taught you guys. And so here, find voltage source, fly over to the opposite side of the circuit. And I see R1 and R2 are connected how? Yeah, parallel. So we start with R1 and R2 being in parallel for number 6. So equivalent resistance is, okay, do product over sum for R1, R2. All right, that's going to go 8 and 10, looks like. So that's 8, 10, plus 10 ohms. That's 80 over 18 is 4.44 ohms. Okay. Right, now, of course, that's not the answer yet. That's just the first step of this method, this process. Okay. Now I'm going to redraw the circuit. voltage source. I haven't touched R3 yet. R3 is up here. Okay, and on my paper, it's this many ohms. Okay. But R1 and R2, well, I've dealt with those collectively. Okay, I just did product over some of those. That's that number right there. Right? Ah, and how do those connect to R3? Is that series or parallel? Definitely series. So can I just add them up? I can, right? So now the total equivalent resistance is just add them up. While you guys are finishing that one, I want to remind you guys that, or maybe it's a new point. I forget if I said it. I've been making a lot of analogies of electricity to like pushing water through a pipe system. I've been talking about like this analogy of traffic flowing around roads and stoplights. You can actually apply this circuit math to those scenarios. So if you are a water systems engineer one day, you got some crazy pipe system, you're trying to figure out how's the water flow with these different pressures. Or if you are a traffic engineer one day, you've got some crazy road system and so many stoplights on all these streets. How's the traffic going to flow and who's incentivized to do what? Rush hour, but you can actually use the same circuit math to those scenarios. Okay. Okay. You guys ready for number 7? Number 7. All right, let's do it. Number 7. You saw there was also 2 dim bulbs and 1 bright bulb, kind of like number 6, except the dim bulbs weren't as dim as they were number 6. So that's kind of interesting. Hold on to that idea for the future. Okay. So find your voltage source, fly over to the opposite side of the circuit. I'm looking at R1 and R2. Those were R1 and R2. How are those connected? Series or parallel?
Oh, just series.
Yeah. Okay, yeah. So everybody's saying series, right? Okay. Because whatever electricity happens to make its way to this part of the circuit, and not all of it will, but any current that does have to go through both R1 and R2 sequentially, right? That means it's series, right? Guess that? If you like trace with your pen. So number 7, let's start with equivalent resistance R1, R2, just by adding them together. Okay. So what are my numbers? Looking at, see, 7 ohms and 8 ohms. So do 7 ohms, 8 ohms, looking like 15 ohms of equivalent resistance. Right? Now that's just the first step of this method. Okay. Then I need to go back and redraw the circuit. Right, voltage source. Right, R3 I haven't touched yet, so we write this guy in. It's 9 ohms on my paper. But R1 and R2, well, they were in series, and I found that to be this many ohms over here. Right? And those 2 are connected to each other. How? Series or parallel?
Parallel.
We're back to a parallel relationship, right? So okay, just do product over sum and call it a day. Let's do that. So the total equivalent resistance then is going to be product over sum. Number of ohms. Right. You guys got all that? So, all right, so we're going to do 1 more of these, and then I'll switch over and show you guys Kirchhoff. Okay. And so number 8. Ooh, got 4 resistors here, and they're all. Right. How are these connected? Let's see. Yeah, well, let's get a game plan, then I'll show you guys the lights, and then we'll go back and solve this thing. Okay, so I see a voltage source here. I'm gonna fly over to the opposite side, which is like R2. You guys see R2, right? Okay. Then work my way back. I'm gonna bump into R4, and these two are connected. How series or parallel? Parallel, yeah, because whatever electricity happened, well, yeah, okay, the electricity would have to split, right? Gets pushed through both simultaneously. That is parallel. Now, after we solve those, how are those connected to R1 and R3? Would be series from that point, wouldn't it? Okay, I wonder what this is going to look like. Hey, where's my? Hold on. Oh, yeah. Okay, I do have this wired up, but I think one of these bolts is actually busted. So, yeah, let me see. It's gonna show me. Sure is. You know what? Let me pull this guy out of here. Let me see if I can show you guys this. You guys to see what this looks like. Okay, I think this should do it. Okay. So I got one bulb is connected to one lead, another bulb is connected to the other lead, and then there's two in parallel connecting in the middle, like to bridge it. Right. Ah, no, still one busted. What? Ah, there we go. There we go. All right. See how the middle two, they're so dim you can barely even tell that they're on. Right? But there has to be electricity going through those that almost look dark, because if it wasn't, then the other two wouldn't be lit up at all, because it wouldn't be a closed circuit. Yeah, so there's two that are clearly on but kind of dim, and there's two that are extremely dim, and you could like barely even tell there's anything going on, but there has to be electricity going through it. Okay. Right, that's what we're about to solve right now. All right, so I had a game plan for this, so let's stick to that. R2 and R4. It's number 8, right? Number 8. So parallel, it's going to be product over sum. So for me, it's 8 and 5. (40/13), right? And if you're an electrician, you probably look right at that, cut straight to, okay, 40/13. Okay. So I've got that many ohms. Okay. Then I'm going to redraw the circuit, just because it's good practice. Okay. Voltage source, resistor, resistor, resistor. Okay. Now all this fun stuff over here I know is 3.08 ohms collectively. It's as if there's one giant 3.08 ohm resistor right there. And where are the other ones? R1, R3 are 7 and 9. Okay, so this guy is 9 ohms, this guy is 7 ohms. Okay. But you guys told me that it's going to be series at this point, because again, start from voltage source. The current has to go through every single resistor sequentially. I mean, treating this guy as a single resistor. Okay. So the total equivalent resistance from the point of view of the battery, or the voltage source, like how much is it pushing against? Be 9 plus 3.08 plus 7. Yeah, there we go. About 19 ohms. All right. You guys see all right? All right. So I know we've taken quite a bit of class today just to find equivalent resistances. Right? But this could be, again, like one part of a larger process. So if I told you this voltage, you could say, okay, I current I here. equals V over R. So you take this equivalent resistance, pop it in there, take the voltage that you were given, which might be like so many volts, like this could be 9 volts, divide by that, you know how much current total flows around the circuit. Now, the thing is, you might wonder then, okay, like I have so many amps going across here, right? But then I remember this was actually a combination of 2 in parallel. So then if you go back to the original setup, the current would actually split to go through 2 resistors in parallel. So how exactly does it split? Well, here's where we need to break out Kirchhoff's rules. Right, we're going to dig down into the circuit and see exactly how does the current flow around a circuit. Actually, Kirchhoff just had 2 rules. He has a junction rule and a loop rule. So I'm going to give you guys a modified version of this in the notes, and just so I can explain what's going on. Okay? So let me start with the series relationship, which I don't think you. Okay, here we'll start with series and then we'll go parallel. So series relationship. Okay. Now you guys know series. Something like this, right? The nodes, again, I'm pulling this out of a larger circuit. Okay. So I'm going to call this resistor A, resistor B, and I'll have some current flowing that I'll call I naught. Okay. So I wonder what is the current flowing across resistor A? What is the current flowing across resistor B? Those are not vector arrows, by the way. Current is not considered to be a vector. And I might also be interested in, hey, what's the voltage drop, delta V, across resistor A? What's the voltage drop, delta V? Okay, delta V, that's like change in voltage, right? As in a voltage drop across resistor B. And also, what's the voltage change from beginning to end? I'll say delta V total. Okay. All right, so they would start with the current here. So current. Because current's real straightforward for a series relationship. And that's just the current's the same everywhere. So the initial current I naught is equal to the current that goes across resistor A is equal to the current that goes across resistor B. They're all equal. See, it's all equal signs, right? Equal, equal, equal. Okay. So if it's like 100 amps, then 100 amps here, 100 amps here, 100 amps everywhere, right? Okay. Right. Now voltage. Actually, I'm going to say voltage drop. Like, you guys remember for current to flow, there needs to be a potential difference. Right? So there'd be a potential difference from this dot to this dot, sort of analogous to a height change if water's flowing. Right? So why does water flow downhill? Well, it's an elevation change. Right? But it's going to drop down in steps. There's going to be a little voltage drop here and a little voltage drop here. Right? So, yeah, how about this? The voltage drop across resistor A, right? Voltage drop across resistor A. Right? Do you guys think it would be proportional to the amount of resistance? For example, right? What if resistor A was like 3 ohms and resistor B was 7 ohms? Do you think there'd be like a little voltage drop across the 3 ohm guy and a larger voltage drop across the 7 ohm guy? Right? Larger voltage drop across the larger resistor? That would be true. In fact, it's directly proportional. And here's how you write directly proportional. Okay. Resistor A compared to the sum of the resistances, all multiplied by delta V total. Okay. There we go. Okay. So if from node to node, let's say it was like 10 volts. No, let's go 100 volts. Let's say it drops by 100 volts. There's a potential difference of 100 volts, kind of like having 11 of these batteries here. Okay. Got 100 volts from here to here. Okay. I've got 3 ohms and 7 ohms. You guys say that there are 30 volts that drop across resistor A and 70 volts that drop across resistor B, right? Okay. And that's another thing I can say too, is that if you add up here, delta V total is just delta VA plus delta VB. Right? So if you add them all up, then has to account for the voltage drop. Right? Kind of analogous to if you had a waterfall that was like 3 meters high here and a waterfall that was 7 meters high here, that corresponds to like voltage drops, right? That the total height change in elevation from beginning to end would have to be 10 meters, right? 3 meters plus 7 meters adds up to 10 meters. Right? Can eventually make some waterfall models with you guys too. Okay. Yeah, checks out. Right, now, everything I've shown you on this page is just for series relationship between resistors. Okay, what happens to the current? What happens to the voltage? Okay. All right, you guys ready to see parallel? You guys ready for parallel? All right, so continuing. Let's go. Kirchhoff's rules, but this time for parallel. Parallel, right? Now you guys know what parallel looks like. So. Call this guy, so like resistor A, call this guy resistor B, right? And then see, there's going to be some whatever the incoming current is, I'll call it I naught. Okay? Well, the current's going to split here, and part of it's going to go this way, I sub A, and part of it's going to split this way, I sub B. Okay, and then also there's some voltage drop from beginning to end across the resistors. Okay. Right, good start. Right, now, this time I'll actually start with the voltage because the voltage is the one that's easier to think of in terms of parallel. Okay. Delta V across resistor A is equal to delta V across resistor B. The voltage drop is the same. Oh, I meant to label that. Oops. Okay, so let me label this out here. Voltage drop is the same. Across each resistor. Right? It has to, remember, voltage is sort of analogous to pressure. Right? So let's say you got a pump pushing through water, something like that, right? Or you got a battery pushing through electricity. Okay? It doesn't matter if these resistors are the same or not. But for example, if resistor A is like 1 ohm and resistor B is like 99 ohms, guys, 1 ohm versus 99 ohms, is it still going to be the same voltage drop across both resistors? Yep. Yep, it's the same, right? But is the current going to split the same? No. So how does the current split? Okay, now this one you got to think on a bit. Right, so this is voltage drop. I meant to label that. It's bothering me. I didn't write that there. Okay. Let's switch over and look at current. Okay. The current. Now, how does the current split? Okay, now this makes sense if you sit down and think about it, but if you're just kind of like leafing through your textbook and you're kind of tired of it, this might look a little weird, but if you think about it, it's like, okay, actually this does make sense. Okay? So how much current flows through, let's say resistor A, I'll say equals, okay. I'm gonna set up a proportion of the total current. It's gonna be some proportion here. Okay. So far this might look kind of like that voltage drop, right? Look, in fact, it's gonna have the same denominator. Add together the resistors. Okay. Now, before I finish this off, because there's a blank up here, okay, I want to see if you guys can figure this out. Because if you guys can figure this out, then well, that's one less memorization because you know how to do this. Okay. Let's say resistor A is like 3 ohms and resistor B is 7 ohms, right? 3 ohms versus 7 ohms. Hey, if you're driving around in a car, you got to go from this point to this point. Right? You know, looking to the left, you see 3 stoplights. You look to the right and see 7 stoplights. Right, so 3 stoplights here, 7 stoplights here. You're probably going to want to take which road? The 3 stoplights, right? In fact, if there's a stream of like 100 cars, kind of like 100 amps, right? 100 cars, most cars are going to split which way? Yeah, like along the 3 stoplights road, right? Okay. Now, at some point, you know, if like all the cars are trying to go that way, you're like, oh shoot, there's no traffic over here. So there's going to be a proportional split. There's going to be maybe a few cars that trickle along the other road because at some point it makes sense for them to do that. Okay? So path of least resistance. So what I'm thinking is most of the current is actually going to go through the resistor of less resistance. Okay. Does that mean in the numerator here, we're about to finish this off, should I put resistor A or resistor B up here? How about this? Let's say we got 100 amps. Got 100 amps is I naught. Okay. Resistor A is like 3 ohms. Resistor B is 7 ohms. I'm thinking most of the current's going to go through the little 3 ohm guy, right? and avoid the 7 ohm guy. Most of it's gonna go through the 3 ohm guy. Right? Right. And so wouldn't the current that goes through that resistor actually be directly proportional to the other guy's resistance? I'm gonna put RB up here. Okay, you guys see that? This is where I'm saying, like, if you leaf through a textbook and you're kind of tired, not really paying that much attention, you might think that's a typo. But if you sit down and think about it, it actually makes sense that the current through resistor A is directly proportional to resistor B. Okay? And vice versa. You could switch the A and the B, and that would be true the other way around. So that the total current I naught is equal to the sum of IA and IB. Right? So now I got maybe 70 amps going this way and the other 30 amps going down this way, but 70 plus 30 adds up to the total 100 amps, right? Guess that. Okay. You know what? I've been labeling these Kirchhoff's rules, but I've been kind of loose with that and give you guys modified versions, right? Here, since we got a minute here, Kirchhoff's rules, actually there's what's called the junction rule. That's what we just did. I'll leave that here, junction rule. And the loop rule, which is actually this one right here, loop rule. Okay. So loop rule technically says this, is that you can start at any point. I mean, this is a modified version of it. It's like, okay, it's the same thing. Right? So you can start at any point on the loop, right? And then as you trace your way around the loop, the sum of the voltages has to be 0. And it would be 0 because it drops one way, but it increases going back the other way. Like if you go with the current flow, maybe it drops, and going against the current flow, it would increase, right? So it zeroes out. This is a modified version of that, right? And then, okay, well, junction rule, well, here's the 2 points, put 2 and 2 together and get that. Okay. Right, you guys get that? All right. Whew. Hit a pause point here. Yeah, a lot of stuff I want to do the next 3 days, so I'll see what I can do. I mean, I want to get you guys this waterfall models. I want to go back to Ohm's law, incorporate that. I want to get you guys a few labs I got set up. So yeah, we'll see what we can do, but that'll be our pause point today.